video tonight on domain and range, you're going to want to fast forward a little bit. I'm going to post an announcement in Blackboard that'll have a link to this very same video, and then you just need to fast forward. I'll give you the time in that announcement so that you know exactly where to start taking notes. Just wanted to give you a little heads up on how this is going to get set up for your assignment for tonight. Everybody see where we're at? So we're now in the purple packet. It's very alliterative. I like saying purple packet. There's a warm-up to kick off this little purple packet. And it's very open-ended. Very, very open-ended. It says, describe that graph. Describe that graph. No pressure. My other two classes today came up with 4 different characteristics for that graph. So let's see what you have to say. Anybody got one of them? Oh, so many hands. Oh my goodness, where to start? I don't know who is first. Is it Nick or Justin? We'll go with Justin. It is continuous. Very good. Everybody should write that down. That is excellent. A couple of you already have that written down. Okay, Justin, how did you know it was continuous? Yeah, it never breaks. I never had to pick up my pen to trace that particular curve. Very good. Okay, what else? Go ahead, Joey. It is a function. How do you know? It does. It passes the vertical line test. I'm just going to take it out a little further than that. What does that mean? Do you remember?
It means or more than 1 point on.
Right. Okay, on the vertical line. Yes, you are correct. Which means that no single input has more than one output, right? In order for it to be a function, every input must have exactly one output. And that's really why it passes the BLT. Very good. Okay, so that was 2. What else? Nick. It is non-linear. Very good. In this chapter, yeah, you only have 2 ways of categorizing functions so far. Linear or non-linear. This, categorically speaking, is non-linear because it does not make a line. That's it. One more. This one we haven't. Go ahead, Mike. We could say it's negative. That kind of pulls in, my other class said that too. That kind of pulls in some connotations about slope that I'd like to steer away from because, as we just said, this is non-linear. We had another word yesterday for like when we saw this downward trend to our graph. Do you remember, Alyssa? It falls, very good, or begins with a D. Decreases, yeah, I like that word, that's my fave. And honestly, it's not my fave, it's like math's fave, like that's the one we'll use the most. So it is a decreasing, non-linear, continuous function. Everybody got that down? Yeah. Does anybody happen to notice anything else? Just curious. Has anybody done domain and range before? Of you have? Okay, I am going to teach this like as brand spanking new. So if you haven't seen it before, don't sweat it. I'm going to teach everybody in the room 2 different ways to think about it. Do you notice how this packet is purple? Purple packet. Okay. Did I tell you that when I photocopy something on colored paper, it's super important because it's like hard to come by? Yeah. This is a paper, this purple packet is something you will keep in your notebook for the entire year. It is a big idea in Algebra 2, not a little one. You want to maybe, like if you haven't stuffed anything in the back pocket of your binder, the back pocket of your binder is a good spot to keep stuff that I expect you to hold on to for a long time. Now, why do I want you to hold on to this for a nice long time? We literally talk about domain and range in every single chapter for the rest of the year. It comes up again. So if you need a quick review, this packet's a good one-stop shop for you. So if you're working on something in chapter 7 and it asks you what is the domain and the range, you're like, oh wait, which one's which? You can just go look in this purple packet real quick. One-stop shop, good place to look. So please keep this packet in a safe place. Okay, so with that, I did see a couple of hands. I'm not going to rat anybody out, but does anybody know what domain is? Does anybody have any ideas? Not a Yeah, it's like the X values. So do you see in the next chunk of paper down, it says let's review. So yeah, a couple of you have that. Domain is just like X values. And over the course, we're going to refine that definition just a smidge. So range is then what? Y values, yeah. So this might be what you have there. Possible X values, possible Y values. I have this little mnemonic device. Mnemonic devices are a way you remember things, maybe like PEMDAS. That's a mnemonic device. Please excuse my dear and Sally. Those are mnemonic devices for the order of operations. For domain and range, I have Dixroy. Dixroy. D, shocker, that's domain. Domain is all about inputs and X values. If I ask you for the domain of a function or for the domain of a relation, I'm asking you to list out for me all of the possible values of X or all of the possible inputs for that function or that relation. Roy, that's range. Range, like domain, very similar, except that it pertains to Y values. Range, collectively speaking, are all of your possible values of Y, or all of your possible outputs for a function or for a relation. Yeah. Well, that's what we're going to kind of talk about. Sometimes we can have every number under the sun, but sometimes our domain or our range can be restricted. And that's actually an excellent segue into what we're going to talk about today. So I appreciate your question, Mackenzie. To be quite honest with you, we don't do a ton of problems today in class. We're going to learn how to write the answer. That's right. We have to spend a good chunk of time just talking about how do you write your answer for domain and range. It's a little dry. I'm going to warn you, it's a little dry. But tonight you're going to do problems, and then we'll practice tomorrow in class. It gets a little more interesting when we start to do the math. The hard part is actually just communicating what the answer should be. I'm sure you'll get very good at it over the next couple of days. Okay, so in the two blanks below, you see I have domain blank and range blank. What I'd like you to do is fill in those two boxes on your own. I'd like you to take a minute, in your own words, give me a definition for domain. And then in your own words, give me a definition for the range. There's little small criteria I'd like you to follow. When you write your definition for domain, I would like you to use these three words in your sentence. And likewise, when you write your definition for range, I would like you to use these three words. So I'll go ahead and give you a second to do that. Just compare your sentences with a neighbor. Make sure each of you has your words. Go ahead. So as I walk around, those sentences sounded pretty good. I walked to the back of the room. I grabbed myself the next thing we have to go ahead and turn our attention to. We are going to construct our very first foldable. And like I said, it's kind of like a way of making flashcards without carrying around extra note cards and things like that. We'll do this a couple times throughout the year. Again, I don't go to the well often, but when I have something super important that I'm going to need you to study, I'll go ahead and grab up one of these. So I'm going to go ahead and show you how to cut this guy. First thing you're going to do is cut off this big white space at the bottom. And that is basically scratch paper. Makes an excellent bookmark. Next, you're going to fold this paper hot dog style. I love that when I say hot dog style, nobody even like flinches. They're like, oh yeah, got hot dog, I got it. Hot dog, hamburger, I know what I'm doing. Oops. That's hot dog. And eventually you're going to paste this guy. You're going to put paste. Don't eat it. I'm just kidding. You're going to put paste on the back. And you're going to paste this into your purple packet. It's going to look like this. And what you're going to see up here in my little physical model here, these are like little doors. So that if you want to know what something is, you could just write your definition and your examples. It's a nice little place to kind of study. It's a everybody see how this is going to look? You're probably saying, Mrs. Lucas, how do I make the doors? Let me show you. So do you see how there's two lines now that are on the cover of your foldable? You're just going to cut those two lines, like so. Have you made these before in any of your classes? No? So yeah, you're going to paste this. Part of your homework tonight is to paste this guy. Now you can staple it, tape it, whatever you need to do. Lick it, stick it. I'm just kidding. That's horribly unhygienic. Do not lick. Do not lick. But yeah, you're going to go ahead and stick this in your purple packet. And we have to start filling this out. Like I said, today is a lot of notation. How do you write your answers? And we'll get to maybe one or two examples in a bit. The first thing that you're going to see on the cover are three different phrases. The top flap. The top flap. So again, you want to put it so that the doors open in this way. Make sure you have the, like it's going to open like a book. Okay. On the top flap, you're going to write the phrase set notation. Those brackets are significant. Symbols in math class are never there for decoration. You might use some flowery language in your English class, some superfluous polysyllabic word choices. But in math class, we're not flowery. Just not. Those symbols are never going to be there for decoration. These brackets right here. So set notation, how do you draw those? Yeah, you're going to have to figure it out. I call them Jay Leno brackets. And there's going to come a time where like somebody's going to, who's Jay Leno? But for right now, I'm rolling with it. See his like big fat chin down here? And like his nose, those are Jay Leno brackets. That's just how, I don't know, looks like Jay Leno when I draw it. So set notation. The next door down, that's where we're going to talk about some algebraic notation. So you're going to see symbols like less than or equal to, greater than, equal to, greater than or equal to. Algebraic notation and set notation are very closely related, if not one and the same. Kind of depends on the problem. And then lastly, we have this thing called interval notation. Interval notation, do you see how I have a square bracket? Not a Jay Leno bracket. This is like SpongeBob SquarePants bracket. So it's squared off. That's also called a bracket, I know. Two brackets today. Oy, oy, oy. Interval, comma, notation, parentheses. Because you could see a combination of those two grouping symbols in any one problem. My stapler still making it around? Yes. Oh, perfect. All right. We're going to open up that top, those flaps, those three flaps, and we're going to fill in 6 rectangles. Do you see the 6 rectangles I'm talking about? Top left, top right, middle left, middle right, bottom left, bottom right. Everybody see what I'm talking about? Okay. We're going to start top left. So when you open it, we're going to talk about when do you set notation, when is it helpful, and when is it helpful to use something else. And, whoops, wrong way. There we go. So, if the graph is discrete, you know what that means, right? Dotted or broken. If the graph is discrete, we're going to list all of the inputs or outputs inside our squiggly brackets, aka Jay Leno bracket. For instance, this could be one way of writing domain as a set. Do you see the big D there? That stands for domain. Domain, for this particular relation, might contain the x values 1, 2, 4, 5, and 7. We're going to add a little bit to this in a few moments, too. So notice 1.5 isn't in there, 2.37 isn't in there, 4.5 4.9 isn't in there. This would be a dotted graph because I'm listing out all of those x values individually. I can't connect these dots. So if your graph is broken, set notation can be super handy. You're very good. Yeah. Next slide talks about, well, what do you do if the graph is continuous? In other words, if we don't pick up our pen to draw it. This is the case where we would want to slide in a little bit of algebraic notation. In other words, we're going to use less than, greater than, less than or equal to, greater than or equal to, because our x or our y values are going to span a space on the graph. So if it's discrete, we're going to list out those individual values. But if it's continuous, you're going to use inequalities in what we call algebraic notation. This looks way scarier than it is. It's going to take a little bit of practice, but I promise you by the end of the day tomorrow, you'll be like, oh yeah, I'm good now. It's just going to take a little getting used to. So the next two slides are a little bit weird looking. So in the next flap, so now we're in the middle left. What I'm just kind of trying to tell you here is that we can use our equality, so our equal signs and our not equal to symbols, and our inequalities, less than, greater than, to describe our domain and range. So when we have algebraic notation, we're talking about using inequalities and things of that nature. And I have all of our symbols that we could use listed here. So less than, greater than, less than or equal to, greater than or equal to, and not equal to. Here we go. Look at that. Okay, these are examples. So the first word you should write is examples. We're in the middle right rectangle. I have 3 examples here. 3. The first one is this guy right here. And I chose this one to be my first example because it is a very common answer. I'm going to read the symbols and then I'm going to tell you what they mean. Ready? So what I'm saying here, this big D, domain, equals means is in math class. So right now we're saying the domain is the set of all x values when x is the set of all real numbers. That is what that sentence means in symbols. X is the set of all real numbers. Super important right there. So what's a real number? Do you know what real numbers are? Real numbers? Anybody? Nope. Very interesting. Kind of a trick question, to be honest. I know I'm not a fan of trick questions either. Real numbers. Mackenzie, do you know? All of them. When I say real ones, any number that would come out of your mouth just now would have been real. Pi is a real number. 3/4 is a real number. -87 is a real number. The square root of 2 is a real number. The square root of 12. Square root of -12. What's that? Do you know? It is an imaginary number. Different number system altogether. We will talk about those in chapter 4. So, it's kind of like the opposite of real. They're called imaginary not because they're from the land of like unicorns and fairies. They're imaginary because they're just not real. talk about them later. So any number that's not imaginary is real. So when do you use this? If your graph literally takes up the entire x-axis, you would use that notation, which is very common. Think about the functions that you graphed in your t-charts last night. And 2, 2. No, 2, 1. I'm sorry, the one I'm about to collect from you. A lot of those take up the entire x-axis. Their domains would be all real numbers. Okay, so sometimes the graph doesn't take up the entire number line, and in which case we have our other two examples. So I'll read those for you too. Here's one right here. Here we would read this as D, that's domain, is the set of the domain is x when x is greater than or equal to 5. That colon right there, or that vertical symbol, kind of interchangeable there, that means when. So here we could say, our domain is the set of values for x when x is greater than or equal to 5. So from 5 on, this graph would hang out. And then I did one with range, because we're going to do both. The range, in this case, just a sample answer, would consist of your y values when y is between -5 and 3. We would include -5, but not include 3. So in general, when you're looking at your algebraic notation that's in those set brackets, the J-Leno bracket, there's basically two parts to what's inside the bracket. Do you see that? You tell me what your variable is. If it's time, you're going to use t. If it's just the plain old x-axis, you're just going to put an x there. So you define your variable, and then you describe where it is on your graph. So you define your variable, and then you describe where it is on your graph. So if you break it apart into smaller chunks, it's kind of not so overwhelming. You tell me what letter you're going to use, and then you describe how it's used with an inequality. The next one that we have is interval notation. This will be one that you use as we move through the year. We get away from algebraic notation and inequalities, and we move into describing domain and range in interval notation. This is something you're going to do more in your trig and pre-calc class and your calculus class. So this gets used more as we move through this class and as you move through math. We use interval notation the most. We're going to practice both. When you have a continuous section of the graph, we write the starting and ending points, and they're separated by a comma. We always write our domain or our range values from smallest to largest. So you write your starting point and your ending point. Smallest to largest. You're going to use parentheses when your point is not in the domain or range. So like if you see open circles on your graph, or tomorrow we'll talk about positive infinity and negative infinity a little bit. And then you're going to have your brackets when your points are contained in the domain or range. So this is what some sample interval notation answers are going to go ahead and look like. Cool. So that U down at the bottom there means in union with. And we reserve that for when there's multiple pieces to our graph. Let's see if you were paying attention a little earlier. This guy right here is logically equivalent to something you already wrote up top. Does anybody know? it's all real numbers. If you're going from negative infinity to positive infinity, yeah, that'd be all of them. That's the whole number line. So you could actually use either of those. If you like the fancy R, use the fancy R. If you like negative infinity to positive infinity, that's also fine. But they mean the same thing. Logically equivalent. I think that's cool too. And we're really just going to do one example. And then the rest of those, I think there's 6 of them maybe, you're going to actually watch tonight. And that's it. It's just up through that 1 page of notes. So it's not a ton. Like I said, the video you should be watching tonight, maybe 18 minutes, 20 minutes in there. So not a ton. You could probably knock out part A on all of these super fast. Because part A is asking you, is it a function? And you folks are so good at that. Everybody see where we're at? Next page there. So in our example, first we're going to do a little throwback and we're going to say, is it a function, yes or no? In part B, we're asked to identify the domain. And in part C, we're asked to identify the range. Okay, first graph right here, I. That would be you. So you're going to pick up just doing these example ones, just those, for your homework tonight. That's going to be the video lesson that you watch. And then tomorrow we come and do some practice. If you just want to make sure the scissors go in the bowl back there,